Hi everyone, this is Yuyan from Google. Today I'll be talking about understanding and improving fairness accuracy trade-offs in multitask learning. And this is a joint work with my colleagues Xuezhi, Alex, Flavin, Jilin, and Ed. Well, fairness has been a pretty hard concept these days, in which we mean we want the model to treat subgroups equally. At the same time, there has been a similarly orthogonal area of machine learning and multitask learning, in which people jointly optimize the performance of multiple tasks. While both of these fields are hard, fairness is still mostly studied in single-task learning scenarios, and multitask learning is mostly focusing on optimizing the accuracy across multiple tasks. So this leaves us with a largely underexplored question, which is how does fairness play out in multitask learning? As a motivating example, for a content recommender platform whose goal is to treat different groups of users and content creators equally, at the same time, it is modeling multiple types of user responses in order to surface the most relevant content to the user. Then the fairness of such recommender systems can be translated into fairness of each individual task in a shared multitask learning setting. Well, we conducted some simple experiments in understanding fairness in multitask learning by comparing the performance of single-task learning models and multitask learning models. We can see that in one public dataset, Celeb A, multitask learning actually hurts one of the task fairness, but improves the other task fairness when jointly learning them. And in another example, multitask learning actually hurts the fairness of one of the tasks significantly while improving its accuracy. So this leads us to believe that training multiple tasks together by simply pooling the accuracy objectives may lead to unwanted fairness consequences, which may already be happening today given the large adoption of multitask learning models. And before we propose our treatment, we also propose a set of metrics to measure this fairness accuracy trade-off in multitask learning. So more specifically, if we care about both fairness and accuracy of each of the tasks, this will leave us with a multidimensional Pareto frontier. So we propose to summarize and visualize this by measuring the relative change normalized by the single task learning baselines and then average across the tasks to reduce the dimension. And then by measuring this ARFG, ARE Pareto frontier as proposed here, it will give us an overall fairness accuracy trade-off across all the tasks in the joint learning setting. And in terms of how do we improve the fairness in multitask learning, let's first look at how does single task learning address fairness issues. So in single task learning, a group fairness entails matching the predictions over negative examples across different groups in the training data, which is usually done by adding a group fairness loss computed on the set of negative examples. And if we generalize this to a multitask learning scenario, this would mean that the fairness loss would be computed on the union of all the task negatives. But however, for the examples that are only negative in one of the tasks, say the orange region here, it should be only relevant to the fairness of task 1. But in the baseline method, it actually does not distinguish between all kinds of different examples, which intuitively is a suboptimal use of model capacity. So what we propose is multitask-aware fairness treatment, in which we redistribute the fairness losses according to the data distribution. And specifically, we let the head layers to address the fairness issues that are specific to the task itself, and we let the shared layers to address the fairness issues that are common to more than one task. And during backpropagation, this would simply mean that we let the head layers and shared layers receive different gradient updates from the fairness loss. We conducted some experiments on public datasets with non-fairness concerns, and we used gender as the fairness attribute. And on one of the datasets, UCI adult, we see that our proposed method is able to improve both the marginal Pareto frontier in the sense that it improves the per task fairness accuracy trade-off, and at the same time, it also improves the overall ARFG, ARE Pareto frontier, which suggests that it improves the overall fairness accuracy trade-offs. We have seen this observation consistently across multiple public datasets, as well as multiple fairness loss functions, which confirms the effectiveness of our proposed method. That's all. Thank you.